Well, so to solve for circuits, there's a couple things. First of all, I have these general hints up here. They're not steps, and they're just sort of tips that I found that in my experience help me to remember what to do here. So the first thing I like to do is definitely have the Ohm's law equations available. So however you want to write a V equals I times R, if you want to do the triangle trick, whatever works for you. Current is equal to V over R, and resistance is equal to V over current. So those just help because we're going to need all of those as we go. There's also P equals I times R. We'll get to that later, but our P equals I times V. That'll be for our last column over here. Power is current times voltage. But so that's step one, or general hints number one. Then basically we need to fill in all these blanks here. All right. And so what I like to do is pretty much what I have right here is just follow these. They're not really steps because you're going to be cycling through them as you go. So start by looking to see what givens there are. So the one big obvious one is the 10 volts. That's going to be their total voltage is 10 volts. Okay. Another given is 3 ohms. We'll just go clockwise in order right here. Just kind of seems to make sense to do that for us at this point. So our first resistor given is 3 ohms. Our next resistor given is 2 ohms. And our last resistor is 15 ohms. Nice and easy. We got a big chunk of that data table already filled out, that chart. And we barely had to do any work. So nice and easy so far. Speaking of easies, that's what the next thing is to look for. And I'll explain what that is when we actually get one, because like right now, we don't really have an easy, so to speak. So again, I'll tell you what I mean by that in a second, but calculations. Okay. So calculations are the stuff that I taught you earlier. Basically, it's either using one of Ohm's law's equations to solve for something, or like what we're going to do here, that you could see, we could figure out the total resistance. So what I'm going to say is that's a calculation. We had to actually find the total. So when we're dealing with a circuit that's in a series, when you find the total resistance, all you do is add up the resistors. So 15 plus 2 plus 3 gives us a total of 20 ohms of resistance, and that is our first calculation. Okay, so now you're starting to see how these aren't really steps. They're just kind of like a priority order of what to look for. But we found something new. Okay, this wasn't given. This is the total resistance. Good. Now, if you're looking, you're like, what can we do next? There's no more givens. We got all the givens done, so we could pretty much be done with that one. So what do we do? Well, we have this blank right here, the current, and maybe you picked up on that. We now have a V and we have an R for the total coming out of the battery. So what is the current coming out of the battery? This is what I'm talking about, more calculations, a different type of calculations. So to figure this out, we know that I is equal to V divided by R. So if I take V divided by R, if I take 20, let's do it the other way, 10 volts divided by 20 ohms of resistance, that means that the current here is 0.5 amps for the total current coming out of the battery. Okay, so that's our calculation. One of our calculations we're going to have to do. So let's go back. We've gotten one done. So for each step, let's look. We just finished one off. Are there any more givens? No, we don't have any more givens. But are there any easies? Now, what does Mr. Germ mean by easies? Well, easies are basically following those rules that I taught you earlier. And in this case, the rule is this. In a series circuit, the current anywhere is the current everywhere. Meaning, if we know that the current going through the 10 volt battery is 0.5 amps, that means that the current going through everything is going to be 0.5 amps, which means that we can say this is 0.5 amps because going through our 3 ohm resistor will be the same amount of current. Going through our 2 ohm resistor will be the same amount of current, 0.5 amps. And going through our 15 ohm resistor will be the same amount of current, 0.5 amps. And that's what I mean by easies. I guess there's probably a better word I could use there, but it's easy because it's like once you know the rule, it's a piece of cake. We just got 3 more things filled in, 3 more boxes filled in, and now we're almost done. All right, so And this little arrow here, it was just because that's just to kind of remind me this is the order. We got all these because we calculated the 0.5 amps right there. So you probably figure out what to do next. We go back and say, well, there's no more givens. There's no more easies that I could see. So there's going to be some calculations to do. Okay. And if you look, we could see, well, we've got these 3 voltages being blank, and we've got current and we've got resistance for all of these. V is I times R. So all we have to do is multiply the current times the resistance, and that's going to give us our voltage that goes across each resistor. So in this case, 0.5 times 3 will be 1.5 volts. 0.5 times 2 will give us 1 volt. And 0.5 times 15 will give us 7.5 volts. And we could double check ourselves here because this is a simple circuit and it's wired in series. And one thing we should know is that the total voltage is going to be the sum of the voltage drops across each resistor. So it starts at 10 ohms of resistor, 10 volts of voltage, 10 volts of electrical potential difference, and it drops 1.5 at the 3 ohm resistor. It drops another 1 at the 2 ohm resistor, and then it drops another 7.5 at the 15 ohm resistor. So by the time it gets past there, it should be down to 0. In other words, the sum of all these voltage drops should be 10 volts. And is that true? 7.5 plus 1.5 gives us 9, plus 1 more gives us our 10. So yes, we're good there. Okay. Power. Well, honestly, I just like to leave power for last if it's blank, if it's all blank like this, because now all I got to do is multiply current times voltage. So if I take 0.5 times 10, that's going to be the total power is going to be 5 watts. In other words, the amount of energy usage per time is going to be 5 watts. And so that's going to be the total. So these next ones should add up to this because this is the energy usage, and each resistor is going to use a certain amount of energy per time. And so the sum should be 5. So let's see. Okay, so IV, so 0.5, 1.5 times 0.5, I believe that's going to be 0.75. I probably should check this with the calculator. 0.5 times 1 is 0.5 watts, and 0.5 times 7.5 is what, 3.25. I am going to check that one with the calculator because I don't trust myself here. Times 0.5. 7.5 times 0.5 gives me 3.75, yeah. So 3.75 watts, and I'm just going to sum those up just to make sure. Plus 0.5 plus 0.75 should give me 5. So those are correct. So that's it. That's how you do these. You just look at each blank and you start with the givens. You see if there's any quote-unquote easies. In other words, if you know something, like in our case here, we know that the current anywhere is the current everywhere in a series. If it's a parallel circuit, you're going to know that the voltage drop across each branch will be the same. That would be the easies, and I'll do that one in another video. And then any calculations you need to do. So that's all there is to it.